Hello guys. Last class we have discussed about the energy, potential energy and kinetic energy related to spring. Okay, and we study about the energy versus displacement graph for oscillating spring. Okay, and what we have learned, that how we represent the graph of oscillating spring. Suppose so how we represent the graph. So this is the graph is parabolic. This is a graph for kinetic energy term, and this is for potential energy. Okay, we draw this graph from the relation half of k x m square equal to half of m v square plus half of k x square. By using the law of conservation of energy, we get this. M is a mass of the clock which is attached to one side of the spring. So this is the potential energy graph V, and this is for kinetic energy graph T, and this straight line is for total energy T plus E, because total energy constant, so it is represented by a straight line. So these are the things we learned in the last class, or discussed in the last class. Now today I'll go for an example, okay, which is given in your answer book. So what is the example, or what is the question? That if a system is considered that a spring is attached to a rigid wall, okay, and there is a car, okay, there is a car which is moving with a car of mass 1000 kg, okay, 1000 kg, moving with velocity, initial velocity u equal to 18 km/h. Okay, a car is moving with a uniform velocity this mass, and the mass of the car is 1000 kg. It's moving towards the spring, and what happens at some instant it collide and however it collide or it strike the spring. The moving car strikes the spring. After the collision, what happens? The car will get stopped after some compression of the spring. Okay, so when the moving car strike the spring, what will happen? The car will get stopped. Okay, the car will get stopped after some compression of the spring. We have to find the maximum compression. Maximum compression of the spring for this system. Okay, we have to calculate the maximum compression of the spring. Given the spring constant is how much? 6.25 into 10 to the power 3 Newton per meter. Okay, so this thing they were given. So how it solve this? We know what is the kinetic energy of the car. Okay, the kinetic energy of the car when it strike the spring. Okay, the kinetic energy of the moving car when it strikes the spring, it will be half of m v square. It is the kinetic energy of the car at which it strike or collide the spring. So this is the kinetic energy of the mu square of the moving car of the body. Now we know that from conservation of energy, in spring, what we have, that from the conservation of energy of this energy in spring, we know that the maximum at maximum compression kinetic energy will be 0 and potential energy will be maximum, or it will be equal to total energy of the system or total energy of this body. So from the conservation of energy in spring, what we know, at the maximum compression of the spring, the kinetic energy is 0 at maximum compression, because when the at maximum compression, after what happens, the car or the body will get stopped, and at this time or at this position the potential energy is maximum. Okay, potential energy becomes highest at the maximum compression. Okay, we know this from law of conservation of the spring. So suppose now what to consider, suppose xm is equal to maximum compression of the spring. Xm is the maximum compression of the spring. Then what will be the potential energy? So potential energy at maximum compression will be how much? Potential energy maximum compression will be how much? Half of k into xm square. Okay, this is the potential energy at maximum compression. Okay, so the initial energy, okay, so at normal, at equilibrium position. Okay, so this is the equilibrium position of the spring at which the car strikes. Okay, and after collision, what happens? The spring get compressed up to some amount. Okay, so you have to calculate what is, so this is considered xm, so you have to calculate this xm. Okay, calculate this xm. So now what we have, see, potential energy is maximum at maximum compression, and initially, okay, initially that means at equilibrium position, at, as you know that at equilibrium position what happens? At equilibrium position what happens? Kinetic energy is maximum at equilibrium position, like we discussed in the earlier class. At equilibrium position, kinetic energy is maximum and potential energy is 0. Okay, at equilibrium position, that is at this position, potential energy of the, at this position, potential energy of the body is 0, potential energy 0, and kinetic energy is maximum. Okay, so this maximum kinetic energy will be equal to the, so this maximum kinetic energy will be equal to this potential energy. Okay, so from the law of conservation of energy, what we have? From the law of conservation of energy, what we have? The kinetic energy of the body. Okay, maximum kinetic energy of the body is equal to the maximum potential energy, xm square. Okay, so this we get from the law of conservation of energy in spring, because at equilibrium position what happens? At equilibrium position, okay, the kinetic energy is maximum and potential energy is 0. Okay, if we see the total energy, potential energy is 0 and kinetic energy is maximum. And at maximum compression what happens? Potential energy is maximum and kinetic energy is 0. So from the law of conservation of energy we can say that this will be equal to this. Okay, this is nothing but the total energy of the spring at two different positions, at this initial equilibrium position and at this maximum compressed position. Okay, so these are total energies. So from the law of conservation of energy, this thing we have. So if we solve this, what we get? Action square is equal to m by k u square. Okay, and u is 18 km per hour. If we convert it into meter per second, it will be 5 meter per second. So if we put the values, it will be 1000. Then value of k is 6.25 into 10 to the power 3 into u is how much? 5 meter per second, so it will be 25. Okay, so this thing will get cancelled. So 25 by 6.25. Okay, so if we solve this, what we get? This will be 4. Okay, so xm square is equal to how much? Xm square is equal to 4. So what is the maximum compression? Xm is equal to 2 meter. Okay, so after the collision, the spring, what is the maximum after this collision? What is the maximum compression of the spring? It is 2 meter. The spring will get compressed up to 2 meter when a car of mass 1000 kg moving with velocity 18 km per hour will strike the spring, which is connected or which is fixed with a rigid wall with a spring constant 6.25 into 10 to the power 3 Newton to meter. So this is how we proceed for the problems. Okay, relating to spring. See, when during solving any problem, okay, during solving any problem, you just think about what are the laws or what are the conditions that are applied in the applied in the systems which is mentioned in the problem. See, this problem can be directly solved if we equate half of m square is equal to half of k xm square, like given in our textbook. But we have to understand how these things have come. Okay, what physical laws and what conditions are applied such that we can write these things. Okay, so from the basics you have to clear all the things when you study physics. So next thing is, up to now what we have discussed about the conservative forces. Okay, conservative forces. Okay, work done by conservative forces, this type of things, and conservation of energy, mechanical energy. Okay, this type of things. So there are some non-conservative forces. Okay, conservative force example is gravitational force. Okay, then spring force. Okay, this type of things are, this type of forces are conservative forces, and non-conservative force. Okay, so example of non-conservative force is what? Frictional force. So what kind of frictional force or frictional force is what? This non-conservative in nature. Okay, so another thing during after this we have discussed that we have discussed about the potential. Okay, up to now we have discussed about the potential of the spring. Okay, then potential energy of earth. Okay, potential, gravitational potential. Okay, discuss the gravitational potential. potential, okay, of R, this is represented by M. Potential energy is represented by M. G is then potential energy in spring, okay, which is represented by half of K into X squared. These things, okay. So when we discuss about the potential in case of spring, okay, in case of spring, what we consider that, okay, when we discuss the potential energy, okay, what we have to find, or we have to choose a reference point, okay. During discussing the potential energy, we always fix the reference point, okay. During discussing the potential energy, we always fix a reference point where potential energy is 0, okay. So when in case of spring, okay, in case of spring, for the potential energy is 0 at equilibrium position. Okay, when spring is in equilibrium position, considered at this position, potential energy of the spring is 0. Okay, or during or in a oscillating spring, okay, when a spring is oscillating, okay, what happens when it is oscillate between the region minus x1 to plus x1, okay, at x equal to 0, we have to consider this position as equilibrium position, and what we found that at this equilibrium position, potential energy P is equal to 0. Okay, similarly, in case of gravitational potential of Earth, okay, gravitational potential of Earth, when we discuss the gravitational potential of Earth, we consider that potential energy of ground, potential energy on ground, okay, on ground or surface of Earth is equal to 0. Okay, when we discuss the potential energy with respect to Earth, okay, we consider that suppose this is the Earth surface, then we consider that at ground, okay, at ground potential energy is 0, P is 0 at the ground, and if we move a height h from the ground, then potential energy is mgh. Okay, so this thing you have considered in case of gravitational potential energy of Earth. Okay, similarly, when we discuss about the gravitation, okay, when we discuss about the gravitation, how we define the potential energy of a heavenly body or potential energy of a body, okay, how we define that. Suppose there is a planet of mass m, okay, so how we define the potential energy of this planet, okay, so what we define the gravitational potential energy. Gravitational potential energy of this mass m is how much? In case of when we discuss the gravitation, how we define that. So when there is an object of certain mass, there is a gravitational field, okay, gravitational field is generated, or there is always gravitational field around this mass, okay. So gravitational potential energy in terms of gravitation, how we define that at infinity position, at infinite position, potential energy is 0, okay. In Earth system, how to consider the potential energy at the surface of Earth is 0. Okay, now when we discuss about the gravitation, when we study about the gravitation, okay, and we will get the terms, the potential energy of a planet, the gravitational potential of a planet, okay, potential of sun, in those type of things, we consider that in that type of things, that potential energy at infinite position is 0. Potential energy of a mass, how we consider that? How we define the reference point that at infinite position the potential energy is 0. Okay, and potential energy at certain point, okay, at the distance r, for this mass, so gravitational potential energy for an object of mass m at a distance r from it will be how much? It is the work done. It is the work done in bringing the object from infinity to this position. Okay, so in terms of gravity, when we discuss about the gravitation, I go in a chapter of gravitation, we will get that potential energy for a gravitational potential of a mass m at a distance r is defined by work done in bringing a unit mass. Okay, work done in bringing a unit mass from infinity to this required position or experimental point. Okay, since we have considered that at the infinite position potential energy is 0 for gravitational potential energy is 0 for certain mass. Okay, so this is how we take the reference or zero potential energy point or position of zero potential energy as per requirement of the system, or depends upon what we have discussed. Okay, now there is another problem which is given. Like the earlier example. Okay, suppose same example, a spring is attached to a rigid wall. Okay, and a car of certain mass, okay, suppose mass is m, is moving with initial velocity u. Okay, moving initial velocity u, strikes the spring. Okay, you have to calculate the maximum compression of the spring, where k is the spring constant. Okay, spring constant. Okay, and xm is the maximum compression. Xm is the maximum compression of the spring. So here there is another condition, that the surface at which the car is moving is not smooth, it is rough surface. Okay, then what is the coefficient of friction? Mu is the coefficient of friction of the spring. So the coefficient of friction between the car wheel and the surface is mu. So in this case we have to calculate the maximum compression of the spring. So in this type of problem, so see, frictional force is non-conservative force. Okay, so earlier the force, all the force that we have discussed, that spring force was that spring force, which is conservative in nature. Okay, F is equal to minus k, which is conservative in nature. But here another force is appearing, which is frictional force. Okay, and this is non-conservative in nature. Okay, so how we solve this type of problems, or how we go for this type of problems? So see, the mass of the body is m, so there is a gravitational pull mg will be on the body. So here in this case, the change in kinetic energy of the body, okay, after maximum compression. So see, change in kinetic energy means initially the kinetic energy of the body is how much? Change in kinetic energy means k final minus k initial. So initial kinetic energy of the body is half of m u square, half of m u square, at which it is moving or at which it strikes the spring. Finally, after action compression, the body will stop. Okay, v will be 0, velocity will be 0. So at maximum compression, what will be the kinetic energy of the body? At maximum compression, we know that the kinetic energy is 0. So k final is 0. So from here the changing kinetic energy of the body is how much? Minus half of mu square. Okay, this is the changing kinetic energy. Now up to now, how do you know? Changing kinetic energy is minus half of mu square. Okay. Now see, work done by net force. Okay, what does it mean? Okay. So work done by net force means, see, when the car collide or strike the spring, okay, it experience or exert a force in the spring, due to which it get compressed. Okay, when this car strikes or collide the spring, it will exert some force. Okay, it will exert some force due to which it get compressed. Okay, so there is some work done. Okay, there is some work done by this system. Okay, there is some work done by the system on the spring. Okay, so when it strikes the spring, okay, at certain position, suppose it hit the spring. Okay, suppose the car hit the spring. So what happens? What are the forces that the body or the car will experience? That the first force is, okay, force due to spring. Okay, this is kx. Okay, this is spring force. So the car will experience the spring force. Okay, and another force is what? It is frictional force. Okay, so or you can write the spring force Fs. So when a car hits the spring, okay, when the moving car hits the spring, so car will experience force opposite to its motion. And what are the forces? The spring force, okay, and the frictional force. So the work done, net work done, so the work done by the work done by net force will be how much? W is equal to minus half of k xm square. Okay, so at maximum compression, xm here, xm is the maximum compression. At maximum compression, work done by the net force. Okay, what will be the work done by the net force? It will be minus half of kxm square minus work done by frictional force. Okay, so work done by frictional force will be how much? So force due to friction will be how much? Mu mg. Okay, so minus mu mg into xm. Okay, this is the displacement of the block or displacement of the car after it hit the spring. So work done by the net force is this much. Okay, so since from the work energy theorem, what we have? Changing kinetic energy is equal to work done. Okay, so from here you can write half of m square is equal to minus half of k xm square minus mu mg into x. Okay, so what we get from here? The minus will be get cancelled, then this xm. Okay, So if we take all the terms to the right hand side, it will be k xm square plus twice mu mg into xm plus minus mu square is equal to 0. Okay, so this is nothing but this is a quadratic equation. Okay, like we have discussed x square plus bx plus c is equal to 0. How we solve this? X equal to minus b plus minus root over b square minus 4ac by 2a. Okay, so this is same type of things. Here we have to calculate the xm. Here unknown quantity is xm, this xm. So here a is k, mu mg is b, and this part is c. So if we solve this, what we get? Xm will be how much? Minus b minus 2 mu mg. Minus b plus minus root over b square means 4 mu square m square b square minus 4ac. Okay, 4ac means 4 mu square minus m square into k, or you can write it will be minus, that will get plus 4 mu square k. Okay, by 2k. Okay, if we take the 4 outside, then all the 2's will be get cancelled. And C, you have to calculate the maximum displacement. Okay, so here this term, okay, here this whole term is greater than this term. Okay, so if we take the negative, negative one, okay, so what it will be? Xm will be the compression, or the xm will be how much? It will be negative. Okay, if we take this, so if we take this plus minus, okay, if we take the minus part, what happens? Xm is negative. Okay, but here we have not considered any reference point or equilibrium point such that x equal to 0. Okay, we have not considered an equilibrium point here. So here we have to consider any equilibrium point, so we are taking only the positive part. Okay, so one more reason that for what we have considering the positive part only for this term, b square minus 4ac, because see, earlier what we have get, maximum compression xm is how much? Earlier when mu is equal to 0, maximum compression was how much? Root over m by k into u. Okay, root over m by k into u. Earlier this was the maximum compression where mu is equal to 0. Okay, so from common, if we see from common sense, we can get that after since the frictional force is opposing the compression, frictional force is opposing the compression of the spring, so the result after considering the friction, okay, must be less than, okay, this compression. Okay, this result, suppose this in xm dash must be less than, xm dash must be less than the case where there is no friction. Okay, See, if we consider the negative sign, so what will be the maximum compression? Minus mu mg minus root over mu square m square g square plus mu square k by k. Okay, so this will be the maximum compression when we consider the negative term, okay, or the other result, okay, the minus the minus part. Okay, this will be the answer. So see this maximum compression term. Okay, this maximum compression term, the magnitude of this maximum compression term is greater than the xm. Okay, so this cannot happen. Because frictional force is exerted, the force of friction is exerted opposite to the, or this force is opposing the compression of the spring. So the compression when you consider friction must be less than the earlier case where xm is equal to root over m by k into u. Okay, so that's why we consider only the positive term or positive part. Okay, so this will be the maximum compression when I consider the friction. Okay, so this will be the maximum compression if we consider the friction in the surface. So here if mu is equal to 0, okay, what we get? Xm will be how much? Root over m by k into u, like in the earlier case. Okay, when mu is equal to 0, we'll get this. So if we put the values, what we get? Maximum compression will be how much? If we put the values and solve it, we will get 1.35 meter. Okay, so this is the maximum compression if we consider the frictional force in the friction in the surface. So this will be the maximum compression if there is friction. So see, this result is less than earlier one. Earlier we get 2 meter. Okay, so if there is friction is present, then work done by the net force, okay, for compression of the spring, work done by the net force for compression of spring will get lost, okay, due to some part of the energy will get lost because of the friction. That's why we get less amount of compression when we consider the friction. Now so this is the thing, okay, when you consider the friction, non-conservative force friction in the system, or if you consider system without friction. So if you consider the non-conservative force, okay, if you consider the non-conservative forces, then what will be the work energy theorem? Okay, okay, if we consider non-conservative forces, okay, see in the earlier case, okay, when you consider the friction, how you represent the work done by net force? It is work done by conservative force plus work done by non-conservative force. Okay, like we have discussed in the last problem, work done by net force is represented by how it is represented? Half of k xm square. This is due to the conservative force minus mu mg into x m. Okay, this is because of the non-conservative part. This is conservative part. Okay, this is a work done by conservative force and this is work done by non-conservative force. Okay, so we can write, when there is non-conservative force, we can write work done by net force as conservative force plus non-conservative force into displacement. So this is work done in case of when there is non-conservative force is present, or if we consider non-conservative force in our system. So this is how we present, and from the work energy theorem, what we get, change in kinetic energy is equal to work done. Okay, and work done is what, when you consider non-conservative force, Fc plus Fc means conservative force plus non-conservative force into displacement, or you can write change in kinetic energy, which is Kf minus Ki is equal to Fc plus Fnc, conservative force plus non-conservative force into displacement. Okay, this is equation number 1. Now for conservative force, okay, Fc into del x is how much? Minus del v. Okay, this is 2. Okay, this is what condition for conservative force. For conservative force, okay, we have the condition that for conservative force, for conservative force, what we have, force in displacement is equal to minus del v, or you can say work done by conservative force, W is equal to Vi minus Vf. Okay, so this is the thing we have discussed in earlier classes. Okay, so in earlier classes, what we discussed, work done by conservative force, Wc is change in potential energy, Vi minus Vf. Okay, or this is written as minus delta V. Delta V means, this means V final potential energy minus initial potential energy, change in potential energy, delta V. So if we put this into equation number 1, okay, so putting 2 in 1, what we get, delta K is equal to Fc into del x. Okay, Fc into del x will be minus delta V, minus delta V plus non-conservative force into del x. Okay, so delta K plus delta V is equal to, for non-conservative force, into delta x. Okay, or you can write change in energy is non-conservative force into delta x. Okay, so when you consider, when we consider non-conservative forces in the system, okay, so then what we get, the total energy delta E is equal to F for work done by non-conservative force. Okay, or you can write W and C. This is work done by non-conservative force. Okay, so when you consider a non-conservative force in the system, so what will be the total energy? When the force in the system is conservative, what we have, for the total energy is conserved. Okay, total energy is constant. Okay, or change in energy, in case of conservative force, the total energy is constant, or change in total energy of the system is 0. Okay, when we discuss about a conservative force, in case of conservative force, what we have, delta is equal to 0. It is change in total energy is 0 in the system in case of conservative force. That is, now we can say that total energy is constant. E is equal to constant. Total energy remains constant in case of conservative force. Okay. Now, if there is non-conservative force in the system, or we consider non-conservative forces in the system, then the total energy, then what is the then what we get if we consider a non-conservative forces in the system? Then what we get, that change in energy, change in total energy. Okay, I'm writing this total energy. Change in total energy is equal to the work done by a non-conservative force. Okay, what does it mean? Change in total energy means, suppose this is means E final minus E initial. Okay, this is the final total energy, final energy, and this is the initial energy. So change in total change in energy means E final minus E initial is equal to work done by non-conservative force. Okay, so if there is non-conservative force in our system, then this will be the work energy theorem. Okay, in case of non-conservative forces in the system, so this will be the work energy theorem if there is non-conservative force present in the system, or we consider a non-conservative force that is exerted in the system. Okay, so up to now we have discussed all about the forces and energy, these type of things. Okay, work energy theorem for conservative forces and non-conservative forces, these things. So work energy or theorem for non-conservative force will be what? E final minus E initial. The total energy at final position minus total energy at initial position is equal to how much? Force due to non-conservative force into displacement, or W, work done by non-conservative force. Okay, so this is a work energy theorem in case of non-conservative force, where change in force, okay, where change in force, okay, in final and initial position, or final and initial case, is equal to the work done by the non-conservative force during that displacement. So this is final energy means, suppose the body is moving in certain direction. Okay, so this is what delta x. This is the initial position. Okay, xi, and this is xf. Energy at xi position is ei, energy at xi position is ef. Okay, and the body is moving, but and there is a non-conservative force applying on the body is F and C. Okay, these are non-conservative force applied on the body. So in this type of systems, F minus ER is how much? F and C minus F and C into del x. Okay. Earlier, if there is no non-conservative forces, okay, earlier if the system or if the body, the force, applied force or the force in the body is conservative, then what we get? Ef minus Ei equal to 0. That is, energy is conserved. Okay, energy remains constant, or total energy remains constant, or total energy is conserved. But when there is non-conservative force in the system, the total energy of the body is not conserved, or it is not constant during the whole displacement. And in case of non-conservative force, what is the work energy theorem? The EF minus EI or delta E is equal to work done by non-conservative forces. Now we'll discuss about the different form of energy. Okay, now we'll discuss about different form of energy. So first thing is I'll discuss about the energy. I'll go for internal energy. Okay, so what is internal energy? Every object or every body possesses internal energy, and internal energy rises, or the internal energy is because of the temperature of the body. So every object or every body possesses internal energy because of the temperature of the body. Okay, when we go for thermodynamics, then heat applied on a system or on a body is equal to change in internal energy plus work done. Okay, or this is the first law of thermodynamics. Okay, first law of thermodynamics, or change in internal energy of a system is heat applied on a system minus work done by the system. Okay, so this is the first law of thermodynamics. Okay, you will get it later. So from the first law of thermodynamics, what we get? The change in internal energy of a system is equal to the heat applied on the system minus the work done by the system. Okay, so this internal energy is because of the temperature. This internal energy rises because of the temperature in the body. Okay, see, when we go for when we apply energy on a body, all amount of energy do not do work. Okay, some amount of energy get lost. Okay, some amount of energy get wasted in terms of heat, or in terms of some due to friction. Okay, or in terms of some radiation. Okay, so the energy get wasted when you apply some energy, okay, on a system to do work. All the energy that we have applied do not involve into doing the work. Okay, some amount of energy get wasted because in terms of heat, okay, in terms of radiation, okay, in terms of sound energy, in terms of sound energy, in terms of sound. Okay, in this different from the energy get wasted. Okay, okay, nuclear energy rises because of the fission. Okay, nuclear energy rises because of fission. Okay, this energy is actually huge amount of energy. Okay, and due to nuclear fission, huge amount of energy is generated. Suppose uranium. Okay, so nuclear internal nuclear energy, so suppose uranium 235 92. Okay, when this is a very unstable molecule, unstable atom, sorry, unstable element. Okay, so when you strike it with a neutron, okay, then what happens? It get converted into krypton and barium. Okay, these are lighter than uranium 235, lighter element, a lighter. These are lighter element, okay, along with 2 neutrons, okay. And because of this reaction, what happens? A large amount of energy is generated along with huge amount of energy, okay. And what is the cause of this energy? This is because of the mass energy equivalence. Okay, this mass energy equivalence is what? This is m. This E is equal to mc square. Okay, this is suggested by, or this is suggested by Einstein. Okay, in 1905, this mass energy equivalence is suggested by Einstein. Okay, in 1905. So this nuclear energy, the nuclear energy appears because of the mass energy equivalence. So what does it mean? When this uranium heavy atom break into 2 lighter atoms, okay, when this uranium heavy atom of uranium get break into 2 lighter atoms of krypton and barium, the net mass, okay, suppose this is the final mass, okay, mf, okay, this is the final mass and this is the initial mass, okay. So the initial mass of the whole system, okay. So when a uranium atom breaks into krypton and barium, the total mass of both the 2 atoms, mf, is less than this mass of the initial mass of the uranium atom, or mass of the uranium 235 atom. So this mass difference, what is the difference in mass? Mi minus mf is equal to delta m, okay. This is divided by delta m, okay. This delta m of mass is converted into energy from this relation, okay, from this mass energy, like in the mass energy relation, okay. So what is the energy generated from this reaction? Del m into c square, okay. So this amount of energy is generated because of this fission reaction, this is called fission, okay. So from mass energy equivalence we can explain, that how this huge amount of energy is generated from nuclear fission, okay. And this is equivalent to del m into c square. And